Okay, so we reached here from our last tutorial. That was the class 2A. So we are continuing in this class where we're solving this problem. So we have to find the four roots of the equation. We found the polar representation of our complex number, and now we have to find the four roots. So root z1 is simply found by putting when k is equal to 0. So when k is equal to 0, wherever we see 0 here, we will put, wherever I see k, we put 0 there. So z1 simply becomes e to the power I, 4 pi multiplying 0 minus pi, then all on 8, because 2 times 4 is 8, right? So this gives me e to the power I multiplying this times this becomes 0. So I get negative pi on 8, right? So at this point, I'll get e to the power negative pi I on 8. So at this point, negative pi on 8. So this gives us our first complex number z1. So to find z2, which is our second complex number, 3 pi I all on 8. And simply, my z2 becomes cosine of the expression 3 pi on 8 plus I sine of the expression 3 pi on 8. What about z3? z3 is equal to when k is equal to 2. So when k is equal to 2, I'll get e to the power I multiplying 4 pi, and where k is, I'll put 2 there. So simply 2 minus pi all on 8. This is simply equal to e to the power I. 2 times 4 pi is 8 pi minus pi. That is giving me 7 pi on 8, right? So my third root is cosine of the expression z pi on 8 plus I sine of the expression z pi on 8. Now finally, z4 is equal to when k is equal to 3. So I'll simply get e to the power I 4 pi multiplying 3 minus pi all on what? 8, right? So this is e to the power I multiplying the expression 12 pi minus pi. So 12 pi minus pi all on 8. Getting e to the power I 11 on 8 pi. So my fourth root becomes cosine of the expression 11 on 8 pi plus I sine of the expression 11 on 8 pi. Now this gives us the root of what? Root of unity. Now let's take another problem, but in this problem we are going to look at a complex number, which is the second application of De Moivre's theorem. So application of De Moivre's theorem. So for the second application, you're going to find the polynomial expression. So I'll just take an example so we solve. I have the expression z cube is equal to I plus 1. This is a polynomial equation which demands us that we find all the three roots of this equation. How do we find the three roots of this equation? We can simply apply De Moivre's theorem here. What do? We take the third power on both sides is equal to I plus 1 all to the power 3. At this point, these 3 cancel these 3, and I'll get z to be equal to I plus 1 all to the power 3. Sorry, all to the power 1 out of 3, because I took 1 out of 3 here. Now at this point, let's see how we solve this. Z is equal to I plus 1 all to the power 1 out of 3. How do we solve such a problem? We need 3 roots of that equation. To do that, I have to convert my I plus 1 to polar form. And I'm going to get my R of 1 plus I to be equal to root of 1 squared plus 1 squared, giving me square root of 2. Then my argument of my 1 plus I is simply equal to tan inverse of 1 over 1, giving me pi on 4. So I'll get Z to be equal to root of 2 e to the power I pi on 4. But take note, in de Morphy's theorem application, we use the extended arguments. For the extended arguments, we simply add 2 pi k to our normal argument. So this section of the argument will give us all the 4 roots or all the 3 roots or all the n roots of what? Our complex polynomial. So in this case, I'll add plus 2 pi k for my theta, that is the argument. So I'll get Z to be equal to this whole expression to the power 1 out of 3 from this part. So Z is equal to square root of 2 all to the power 1 out of 3 multiplying e to the power I pi on 4 plus 2 pi. 4 times 2 pi k is 8 pi k. So I'll get e to the power I 8 pi k plus pi all on 4. Then this whole expression to the power 1 out of 3. I move to the other section so that I get my Z, which is equal to the square root of 2 all to the power 1 out of 3 multiplying the expression e I. So here I had 8 pi k plus pi all on 4, all multiplying 1 out of 3. 8 pi k plus pi all on 4, all multiplying 1 out of 3, like this. So at this point, I'll have Z to be equal to square root of 2, 1 out of 3, multiplying e to the power I 8 pi k plus pi all on 12, right? Because I've applied the De Morphy's theorem here. I just find my Z1, that's the first root. I need 3 roots since it was ZQ. It's when k is equal to 0. So I just put 0 at this section and I'm going to get, so this maintains, so I'll get square root of 2 all to the power 1 out of 3 multiplying the expression e to the power I, then this is 0, so 8 pi multiplying 0 plus pi on 12. So this simply gives me square root of 2 all to the power 1 out of 3. This becomes pi on 12, e to the power I pi on 12. Then now this becomes square root of 2 all to the power 1 out of 3, open brackets, cosine of the expression pi on 12 plus I sine of the expression pi on 12. And that gives me my first root of this equation. My second root Z2 is when k is equal to 1. I just get my square root of 2 all to the power 1 out of 3 out, e to the power I multiplying 8 pi, k is now 1, plus pi, everything on 12. 8 pi plus pi is 9 pi, all on 12. So I simply get square root of 2 all to the power 1 out of 3, ei, that is 8 pi plus pi, that is 9 pi, all on 12. I simply express my Z2 to be equal to square root of 2 all to the power 1 out of 3, e to the power, checking what I have here, I to the power 9 pi on 12, I 9 pi on 12. So this amounts to square root of 2 all to the power 1 out of 3, cosine of the expression 9 pi on 12, plus I sine of the expression 9 pi on 12, giving us the second root. Z3 is given when k is equal to 2. I simply get square root of 2 to the power 1 out of 3 e to the power I 8 pi, then the k becomes 2, right? Plus pi all on what? At this point, all on 12. So all on 12 this way. And I'll be getting root of 2 all to the power 1 out of 3. Then this side I get 8 to 16 plus 1, 17. So e to the power I 17 pi on 12. My third root simply becomes square root of 2 all to the power 1 out of 3. Cosine of the expression 17 pi on 12 plus I sine of the expression 17 pi on 12. And that gives me